Okay, so I want to see if I could show you one way of doing this. This is section 6.3, number 17. Assume that the Richter scale magnitudes of earthquakes are normally distributed with a mean of 1 and 131 thousandths and a standard deviation of 531 thousandths. Complete the parts A through C below. Now I know that they're already answered, but we're going to talk about this one specifically, and we'll just go ahead and hit them all to be sure that we're on the same page. You can do these with the tables out of the book, or you can do these with technology. Since I'm assuming most of you guys want to know how to use the technology that's most convenient, I'm going to use StatCrunch. Okay, Earths with magnitude less than 2 are considered micro-earthquakes and are not felt. What percentage of earthquakes fall into this category? Right, essentially what they're saying is use this cutoff score on the, where is it again, normal distribution, and you're going to have to standardize the cutoff score because it's not on a standard scale already. If it was standard, we would know that because the mean would be 0 and the standard deviation would be 1. So we're going to have to convert it to that and then find out how much area is under the curve from that point, which we're saying less than the amount of shaded region under the curve, 2. So less than 2. All right, and obviously, you know one thing for sure, it's going to be above 50%, right? Because if 1.131 is the middle of the distribution, because that's the mean, then anything above 1.131 is going to be above 50%, since we're shading from the left, the less than side. All right, without any more talking, let me just go ahead and click on StatCrunch. Okay, hit Stat. Choose one of your calculators. And the one we want is a normal calculator. That's the normal distribution. Now, by default, it starts out with the standard normal distribution, C, 0, and 1. But we can actually just change it to whatever distribution we want. And so, I mean, it's still a normal distribution, but what I mean by whatever we want is standard or non-standard. Okay, so here's our non-standard normal distribution. And by the way, they have an option up here. I don't know if you've already noticed this, but if you're going to do an area in between, rather than having to do it the long way that you'd have to do it if you're using the table, meaning the book, the paper table, rather than having to find the area all the way over to the left and then behind from the bottom to the left and subtracting, this allows us to do what the calculator does. That's a pretty new feature. And it got really exciting when they put that in there, because then that meant we could pretty much use StatCrunch for everything. All right, here is the statement less than or equal to. And notice, by the way, that this is appropriate that they're using an X and not a Z, because we're not on a standard Z-score, standard normal distribution. But they could leave an X there instead of putting a Z, even if this was 0 and 1. Just trying to help you follow the notation here. So this is saying what's the probability that you could be less than, this, you're looking at all cases since X is a variable, where you're less than or equal to 2. Hit compute, it'll draw the graph, that's what I love the most. And you see there that we've got rounded 0.95, and obviously she already got that. By the way, this is the empirical rule here. 68, 95, 99.7. So if you want to see those ticks there, you can put them in, and it'll show you even more detail. It's pretty cool. You don't need them. Okay, so now remember, with area scores, we usually do 4 decimals, so 9,491 10,000ths. But then, since we're going to put this in percentage form, we could have put 9,000 or 94.91%. Now, theirs does not say that, but they would have taken that answer that we had in there. on the table here, let's see. And this is probably a good one to demonstrate using the table because it's a less than statement, which means it's a left tail. And that's how this table information is given. It's always given with cumulative area from the left. So here is the negative side when you fall on the left side of the middle. And then here's the positive side. That's where we want to go. And we're not going to be able to look up an x-score of 2 here because these aren't the x-scores, right? These are the standard normal distributions, which mean that the mean is 0 and the standard deviation is 1. I've said that like 3 times, I know, but I'm trying to reiterate it. So let me find out what would the z-score have been for a score of 2. You don't need those zeros, by the way. Okay, so you take the x point, you minus the mean, x bar, and you divide that whole result. So I'll just go ahead and hit equals first, because I wasn't using parentheses. Make sure you're using the correct order of operations. And then you divide by the standard deviation for the set. So I should be looking up 1.64, essentially. That's going to make it come out higher than the score that I found out when I was being more accurate with the StatCrunch, because StatCrunch and Excel and TI-83 can be more accurate. This thing is doing all the integration of the curve, and that's meaning finding the area under the curve, but it's doing it once to this level of accuracy, and you're jumping points. So you're not going to be as accurate with the table. But that's okay. I'm just trying to show you why they had 95. Alright, so here's 1.6, right? A z-score. And by the way, that is the z-score now, right? Because we just converted it by taking 2 minus 1.131 divided by 0.531. Okay, here is 1.60 flat. Here's 1.1 and 61 hundredths, 1 and 62 hundredths, 1 and 63 hundredths, and we were above that. We're actually in between these two. So we got to go to this one because conventional rounding would have taken us to 1 and 64 hundredths, which was 94.95 as a percent. And that's why they put in that percent. All right, but don't worry. If you put in the StatCrunch answer, it will give you full credit. All right, then they ask, earthquakes above 4 will cause indoor items to shake. What percentage of earthquakes fall into this category? So again, go to the curve, find out greater than 4. Now this is where StatCrunch is such a huge help, and the technologies, because remember, this one only finds area to the left. And I know this is something you know if you already know this, but if you don't know this, I'm sorry. I'm saying it for everyone. Okay, so what you would have done is you would have found up to 4, the corresponding z-score, and then you would have taken 100% of the curve minus that percent from the left. That's called the complement. So you've taken 1 minus whatever decimal percent that is, and you have gotten the area up here. I'm not going to waste my time with that because on StatCrunch, which I already have open, already have that mean that corresponds to our problem and the standard deviation that corresponds to our problem. I can just click this and say 4, oops, I mean 4, and then choose the percentage greater than. Alright, look what I get. 0.0000000, you know, and then 3. So to 4 decimal places and then put it into a percentage form, this would be 0. And you could have actually put that in for your homework. I promise it would have worked, and that's what I did when I did it. Okay, but the answer on here, the highest we can go is 0.9999, and that's at 3.5. Now, I didn't check to see what my corresponding z-score was, but I can do that really fast. So 5.40 would have been our z-score that corresponds to a Richter scale 4, and that is way off the chart. And that's why we saw 0, 0, 0, 0, 0, you know, and which would have been 0%, but this doesn't go that to that level of accuracy, which is fine. So that means that if you want to just default to the table answer, you just say, and I'll show you what we did say. You can just say 0.01, right? 0.0001. Move it over 2 decimals, 0.01. Got it? Okay, now let's flip the argument all around. So instead of looking at Richter scales and finding out the percentage of occurrences or probability for them to occur, let's look at the 95th percentile. So we want to find out what is the cutoff score on this distribution that contains 95% area or 95% coverage underneath the curve, and that's meaning from the left. That's referring to the bottom 25. If you don't remember percentiles, go back to chapter 3 where we learned about percentiles and quartiles and so on, and the 5-member summary. Okay, so I'm going to look at my distribution here, and this is a great thing, again, as if I'm practically advertising for this software. I'm going to go ahead and say, look, cut that out. I don't know where that's going to occur. Put it back on a left tail, so that I'm determining left area. And fix this so that it's at 95%, 0.09500. And what this will do is it'll draw that distribution, and in order to draw that distribution, it's got to show me this cutoff score, right? So I hit it, boom. Remember, this is my mean and this is my standard deviation. And look where it put it. It put it at 2.004. Nice, right? So that would be my answer, right? All right, what about if you're using the table? Maybe you think I've got something up my sleeve. Okay, so we're trying to turn this around. That means that we've got to come inside the body this time instead of going out around the peripheral and looking at the z-score. We're going to go inside the body. We're going to find 95%, which is right there. You'll notice they've got that specially marked as 1.645, so we can go out to that level of accuracy. But that is a z-score, not an x-score. So we're going to turn our calculation around, and where before we would take that our x-score and we would subtract the mean of the distribution and divide by the standard deviation, we're going to turn that all around now, and we're going to take the z-score, and when you turn it around, I mean using algebra, so the first thing you need to do is turn around the division, because that was the last thing that you did in the regular calculation. So I'm going to turn around division by inverting and multiplying by our standard deviation. Okay, get that number. And then the first thing we had done was subtract, find the deviation between data points and the mean. So the next thing I'm going to do is undo the subtraction, which is add. So I'm going to add the mean of the set. And look what I've got. 2.004 blah, 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 blah. See how that works? Now, I think what may have ended up happening, because you said your answer was lower, you may have ended up not seeing a 95 and thought, well, they kind of go right between, so I guess I could choose this one or that one. And you chose this one, and you got a lower number. In fact, let me just go ahead and run out the calculator on that number and see what would have happened. 1.64 is our corresponding z-score for a 94.95% from the area, or the body of the area scores. Multiply the standard deviation, add the mean, voila, your answer revealed. So that's what you must have done. Unfortunately, the homework wasn't going to accept something that far away from the answer. And you nailed that last part, so I'll just, nothing to say there. But I would like to return to the formula sheet just to give you a reminder. If you can't remember then at least to resource during the test. Here's the z-score calculation, and you just have to turn it around when you're trying to find the cutoff score while knowing the area that you want to pin in between